This is the problem example on locating a shear center. So let's go ahead and take a look at the problem first. Try to understand what it is before going and punching in the numbers and finding the shear center. So what you are shown is a cantilever channel section similar to what we saw in the lecture, where at the end you're applying a load of 10 kilonewton, a vertically applying load of 10 kilonewton. Now as a result of this, we have seen that internally you develop these kinds of forces that are there, which results in bending as well as twisting. So it results in the twisting. Now you're supposed to find the shear center, that is essentially where you have to apply the load P. Now we have seen we have to apply the load P somewhere over here to find the shear center E. Remember, E is the distance at which you're applying the load P such that your element or your beam just bends and no twisting happens. Now some of the properties are given for this one. You are given the properties of the channel section, the height and the width and so on. This is an enlarged view of this section over here. So it has a width of 100. This is the centroid where your load is acting over here, and the thickness is 4 mm thickness. So it is a thin walled section that you have over here. Now from this you can easily calculate this area moment of inertia, which I have not calculated separately, but this is a given for this problem, so you can utilize this one over here. Okay, so now for this, let's go ahead and first find that where the shear center of your particular beam is going to be. Now remember, one thing is that these are the forces which are acting in the flange, and this is the force which is acting in the web, which is equals to the applied force P over here. So the first thing to find is these forces which are acting over here. So if you recall that these forces are designated by F of F, right, where this F of F times this vertical height H was equals to P times E to derive the shear center, right? So we have to find this F of F, right? Now to find this F of F, remember the precursor to that is to find the shear stresses. Now we know the shear stresses here is going to be a linear variation because it is perpendicular to the direction of the shear. The shear is acting vertically up at that internal section. So it is going to be it is going to have a linear variation over here. It is going to have a parabolic variation and a linear variation over here, right? And the overall direction of the shear flow or the shear stress is going to be what? It is going to be somewhat like this over here. So we are going to have smaller arrows over here, to bigger arrows, to big arrows, then maybe a bigger arrow over here, and so on. So something like this. This is going to be your overall direction of your shear flow. So let's go ahead and first calculate Q, because Q is related to tau. That will give us the shear stress which is acting over there. So for this, I'm going to take a small chunk. You can either start with a small chunk over here. Usually what I like to do is that from where the shear flow is moving away, I like to take a small chunk over there. You can either take a chunk here or take a chunk over here. The only difference it is going to do, you may think it is going to do, is in calculation of that capital Q, because Q, small q equals to V times capital Q divided by I. But either way, you have to consider for that capital Q, that area that you get A prime times Y bar prime. It is only whatever makes your calculation convenient. So I'm going to start by taking maybe a small chunk over here. So let me take a small chunk. So this is the chunk which I'm going to consider, and let's say this guy is at a distance S from here. Say this distance is S, which I have marked. So what I'm trying to find is that at this location, at this S, what is this value of Q which I'm getting over here. So let's go ahead and write that formulation for the Q. So we know that our Q, so this is at the flange I'm calculating. So at flange, so let me go ahead and write that. So at flange, because remember, so this part, this is the flange, the top and the bottom are the flange, and this guy is the web. So at the flange, at this part where I have taken this guy over here, this section, so here I am writing my small q is V times capital Q divided by I over here, right? So now V I know is 10 kilonewton, which is given in the problem. This is the shear force acting. I is also given in this one. So the question is to calculate the Q over here, as we always do. So now for Q, remember Q is A prime times Y bar prime. So here for this small chunk over here, the A is going to be S times this thickness. Remember, the thickness all throughout is 4 mm. So Q is going to be your S times 4. So that is my A prime times Y bar prime, that is the distance of the centroid from the neutral axis. So that is 75 mm times 75. So if we plug all of these guys over here, you get the expression for Q as Q equals to 10, that is the load, times 10 cube. So I'm converting to Newton, times what we just calculated for capital Q, S times 4. So that will overall give you, I have this calculated already, it gives you 0.533 S. So it is in terms of S, because you see, oops, sorry, I wrote that behind my camera, so I will just write it below. That gives you 0.533 S. So it is in terms of S because you have this guy S over here. Okay, so now from here we can tell that at S equals to 0, so essentially at this edge over here, the shear flow Q is going to be 0, and it is going to be maximum at this point D over here with a linearly increasing trend from 0 to here. So let's just write that. So at E, I have my Q. So this is the Q at the flange I'm calculating. So I will mark it as QF. At E, QF equals to 0. So at D, I get it as 53.3 Newton per mm. So this is the Q I'm trying to calculate. From the Q, I'm trying to calculate the stress. So my tau of F is going to be, remember the relationship, Q is equals to tau times T. So tau equals to Q divided by T. That is 13.33 Newton per mm square. Why mm square? Because I divided with another unit of length over here. So here I'm going to have a linear variation. I'm going to draw the figure later. So I know I'm going from 0 to here to a linear variation over here. Right? Now next is, so here at the point D, now when I'm coming to the web, at the point D, whatever was in the flange, just like the flow of water, at the point D I'm going to have a horizontal jutting out portion here as well, which is going to be your 13.33. So my next point of interest is C prime over here, and I know from D to C prime the variation is going to be parabolic. So let me calculate the point estimate at C prime before drawing the figure. So as I said that in the web, so let's just write at web, we get, Q of web at D will be equal to Q of flange at D. That was what we had calculated, that is 53.33 Newton per meter mm. So correspondingly your taus are also going to be same. So I'm going to calculate now at C prime. So to calculate at C prime now, I have to, so I'm essentially trying to find this arrow which is going to happen just leaving C prime. So I have to consider this entire area which is over here, so which is this guy, this area. So for this, I'm going to quickly write the value of Q. I can divide this entire into, write the value of capital Q, I mean. I can divide this entire area into this one chunk of rectangle, another chunk of rectangle. For this rectangle, I can calculate the A prime times Y bar prime, and for this rectangle, I can calculate the A prime times the Y bar prime over. So I'm going to quickly write it. You can go back and check whether it is correct or not. So what I just wrote over here, this bit is for this bottom rectangle. So A prime times Y bar prime, and the next bit is for this rectangle over here. So if I plug all of these guys back over here, let's see what is the value of QW that I get. I get the value of QW as 73.33. So correspondingly, I'm going to get my tau W. This is going to be simply divided by the thickness. So now that I have found what are the values of taus which are going to see, my final objective is to find this force in the flange which is over there. But now since I have found all, and I actually need not have found this one to calculate the shear center, but simply just for demonstration I've calculated everything. Let me go ahead and draw the distribution of the shear stresses across all the faces. So what I have just drawn over here is the distribution of the shear stress that is there. So the shear stress in the flange varies from 0 to 13.33 over here, and from 0 to 13.33. So you just like the flow of water, this ordinate must be equals to this one because there is no extra water coming from anywhere. So this must also be 13.33, and at the center at C prime what we calculated 18.33, this is over here, and from here to here is parabolic variation, and the rest is just a mirror image at the bottom over here. Right. So now our job is to remember, our job still remains in calculating what is this FF over here, right? So that FF can simply be calculated by this shear stress distribution. Now remember, again I'm pointing this out over and over, this is just the representation of the magnitude, not the direction. So there is no direction, the direction is along this one over here. So if this is a tau f which is varying from 0 to having a linear increase over here, how do we calculate the overall force which is FF which is acting over here? So the overall FF which is acting, we can write it as, right, so it is half times 13.33 times B times T. Now you have to try and understand this. So here you see, if suppose if this tau was a constant force, it was not a constant stress, it was not a linearly varying stress, suppose it was a a constant stress, so how will you calculate the total force? How do we get the force from the stress? It is the stress multiplied by the area, right? So here the area is this area, so that area is your this width B which is 100 mm times this thickness T which is 4 mm over here. But here your tau f is a linearly varying force, starts from 0 over here, so it goes up to 13.33. So that is why I have this half of 13. It's like the triangular load kind of a concept over there, right? It is half times 13.33, but the area over which it is acting, it remains the same, it is B times T. So if you plug in the numbers, let's see what we get. So we get 2666 Newton. So now we know to calculate the shear center, we have our formula, that is P times E equals to F times H. Now remember, we are trying to find the E. What is E? E is the, let me just mark over here, maybe E is this distance where I am supposed to apply this load P to resist the twisting which is happening over there. So let's go ahead and plug in the numbers and calculate E. The value of E that you get is 40 mm. So that is the location of the shear center that you have. So essentially, to resist the twisting of of this whole channel section, you need to apply this force P at a distance of 40 mm from this particular edge or from the center line, since it is a very thin section. So this is the E which we just calculated. This is, right? So to resist the bending, you must apply this load P. I will just hypothetically draw this one over here, which acts at this distance E from the edge. So that is how we located the shear center. So I hope this problem example was clear to you on how we calculate the shear center for a channel section. So you can also try out for other kinds of sections which will take a look while solving some of the problems.